Okay, let's quickly recap what we did in the example of the previous video. So we found our center of mass to be approximately 1.44.36. And again, going back to the graph we were looking at, remember this was the function 1 over x. And so at 1 over 1 is 1, the y value is 1, and at x equals 2, when I plug it in, the y value is a half. And again, we said this was kind of left heavy and bottom heavy, so we had guessed visually that the center of mass might be somewhere along towards the left lower region. And the value that we found for the centroid or center of mass is 1.44 for the x value, x bar, which right about there visually is 1.5-ish. It's to the left of it. And then for the y bar, it's about a third of the way up. So it's 0.36, so somewhere along there, a third of the way up. So visually it makes sense, along with our calculations, what the center of mass looks like. Let's go look at another example. Okay, we're supposed to sketch the region and find the centroid or the center of mass. It looks like the equation given is simply an equation of a line, and then it's bounded by y equals 0 and x equals 0. So I'm going to go ahead and solve for y here to be able to graph the line. So in isolating y, our function of x is basically negative 3/2 x plus 3, which we can easily graph to get a visual going. So we got a y-intercept of 3 and a slope of negative 3/2, so down 3, 2 to the right. So we've got this line, and that line is also bounded by this guy that says y is equal to 0, and y equal to 0 is just the x-axis, so at the bottom it's bounded by that. And it also says that x is equal to 0, and x is equal to 0 is just the y-axis, so to the left it's bounded by that, which means the region I'm looking at is trapped between the green, the blue, and the red stuff. So that's the region of interest, and I'm supposed to find the center of mass for it. And so basically where I would position a fulcrum to balance that thing. This kind of looks like it's left heavy, meaning it's got more stuff on the left, and bottom heavy, more stuff on the bottom. And so I'm guessing that the center of mass will be somewhere here visually. It can't be somewhere here because that'll tip it over that way completely. It can't be in this corner because there will be too much stuff on this side. So somewhere maybe along there is the center of mass, but we'll go ahead and calculate it. So from our derivations video, we found x bar to be this integral and y bar to be this integral. And the first thing we're going to do that's going to be easy to get is get the area of the region, and that's just I don't even really need to do an integral to get the area of that region because this is a simple shape. It's a triangle. Let's just use geometry to get the area. So the area of a triangle is a half base times height. The base here is 2 units, it looks like. And the height here is 3 units. So we end up with, I guess, 3 for the area of this region. And again, if you wanted to do it using an integral, that's perfectly fine too. You're looking at the area under the red curve from 0 to 2, because the x values go from 0 to 2, of this red function, and that red function is right here, negative 3/2 x plus 3 dx, and once you integrate, you should get the same thing equal to 3. So whether you use an integral or just look at the shape and recognize, the first thing you want to do is get the area of the lamina you're looking at. Then look at this integral, see what you get, look at that integral, see what you get, and divide those values by the area you found. So it's really a bunch of evaluating integrals. So I'm going to focus on x bar first. It's just 1 over the area times the integral x f of x dx. So the area we found to be 3, 1 over 3, from 0 to 2. Why from 0 to 2? Because I'm interested in this region that has x values going from 0 to 2. And then it's just x f of x. So x times whatever function you were looking at. and the function I'm looking at is -3/2 x plus 3. I put that in, multiply by dx, and it looks like that's going to be a pretty quick integral to do. So it's a third times -3/2 x cubed over 3, so that's over 6, plus 3x squared over 2 from 0 to 2, and that's going to give us a value of 2/3 when we evaluate it. So when you do this integral, since this is just a power function, and I know at this point you all of course know how to integrate this, you might want to just quickly use your calculator, Math 9, and then input -3/2, don't forget to include in parentheses x squared plus 3x, comma, in terms of x from 0 to 2 for your limits of integration. Push enter, and that gives us a nice 2. So this integral was 2, just divided by 3, 2/3. So when you get to here, it's probably best just to use your TI to get it quickly. So we got our x bar, let's go get our y bar. So for our y bar, I have 1 over the area, which is 1/3, the same as before, from 0 to 2. Again, from 0 to 2. And it's a half times your function squared. Remember, your function was just a linear function, squared dx. So you can go ahead and multiply that out and actually do the integral if you want, or since that's going to be a polynomial anyway, we can just put it in our TI. So we'll do Math 9, and I'm going to put this as a -1.5. Let me open up another parenthesis since I'll be squaring it. -1.5x plus the 3, close the parentheses, square it, comma, in terms of x from 0 to 2, close equals. Okay, so this part is just going to be 6, it looks like. So we got, remember, for that part, just a value of 6. So 1/6 of 6, 1. So we got our y bar. So the center of mass for that region looks like it's 2/3, comma, 1. Let's go visually see if that kind of makes sense based on the picture. -2/3. So -2/3, there's 1, -2/3 about -0.67 to the left of 1, and then the y coordinate of the centroid was just 1. So right about there is the center of mass, which is what we had actually visually decided as well, because we said it's kind of left heavy and bottom heavy. You've got more stuff over here than you do over there. So picture wise it makes sense as well. Now let's go look at the idea when you have your region bounded by two curves. So similar to the derivation video that we did of finding the centroid of a region bounded only by just the curve f of x, we can also have the region bounded by two curves. So I could have something like f of x for one curve and g of x for another curve between the intersection points A and B, and then we could be interested in the centroid for that region that's bounded by both curves. So similar to the derivation video that we did before, x bar will end up just being 1 over a from a to b of x, not just times f of x, but f of x minus g of x dx, for us to be able to get that part of it. So it'll be top function minus bottom function, f of x minus g of x. So it's very similar to just x times f of x, but to get that length, we end up subtracting the two curves. And similarly, y bar will be 1 over a of course being the area between the two curves, from a to b, of a half, not just your function squared, but f of x squared minus g of x squared dx. So we alter our formulas a little bit and get the centroid, where a, of course, here is the area between the two curves. So let's go look at an example where we look at a region that's bounded by two curves. Okay, we have find the centroid of the region bounded by these two curves. It looks like it's just a line with a positive slope and a parabola opening up. So rough sketch is an opening up parabola, and a line with a y-intercept of 2. So we're interested in something like that. We can also go put that into our TI. Let's practice that so we can get some accurate points. So we got y1 is x plus 2 and y2 is just the x squared. Let's do a zoom 6 for a standard window. There's our line. There's our parabola as we had suspected. So these two intersection points are going to be important because that's going to tell us where our bounds of integration or limits of integration will be. So we can use the isect feature, second trace, intersect, and I'm going to get closer to the left intersection point, push 1, enter, it says second curve, I push another enter for the second curve, and it says should I guess, I push enter again, and it gives me the left intersection as negative 1, 1. I will do the same for the right intersection point, second trace, push 5 for intersect, move your cursor closer to the intersection point of interest, push 1, enter, push another enter, and push a third enter, and it should give you the right intersection point, which is 2, 4. So you could use your TI to get the intersection points quickly, or just use algebra by setting these two equations equal to each other, just doing a substitution method. So algebraically, y is equal to that, y is equal to that, then these guys must be equal to each other. Set them equal, move everything to one side, factor it out, and you get the same intersection points, negative 1 and comma 2. So I don't care whether you use your TI or you show it algebraically. So we got the left and the right locations for us to be able to start integrating to get the area. So if you remember from 261 or Calc 1, this is the area between two curves from negative 1 to 2. Basically, it's a top minus bottom type of problem. So top function was your line, and your bottom function is your parabola, top minus bottom, and do that integration. So if that's a simple polynomial, integrate from negative 1 to 2 is 9/2, or since it's a simple polynomial, put it into your TI and get a 9/2 for your area in between the curves. Next, we'll find x bar, which is just 1 over the area, and then x times the difference of the two functions. So 1 over 9/2, the area, from negative 1 to 2, our limits of integration, x times the difference of the two functions. Top is x plus 2, bottom is x squared, another polynomial, easy to evaluate. So 1 over 9/2 is just 2/9, and then this polynomial integrated quickly with your TI will just give you 9/4. So either by hand or with your TI, your choice. So 2/9 times 9/4, and it looks like we get a half for x bar. Let's go find y bar. So same idea, but take your function, top function squared, and subtract from it the bottom function squared. So we got 1 over 9/2, again from negative 1 to 2, a half times the top function was the linear function squared, minus the bottom function was the parabola squared. And again, go ahead and use your TI. And in using my TI really quickly, I got 72 over 5 for this integral. So this is going to give me 2/9 out in the front. I hadn't used the 1/2, I'll keep that as is. And then the integral of this guy was 72 over 5, so I end up with 1.6. So the centroid of that region, we'll go look at it visually too to make sure it makes sense, is a half, comma, 1.6. Let's go take a look at, hopefully our graph is accurate enough for it to make sense. So half and 1.6. Oops. So a half to the right and 1.6 up. I'm going to draw a more accurate graph to make sure things make sense, or maybe even let's go look at our TI. So I've zoomed in on our graph, x plus 2 and x squared, and our centroid was 1/2, so about there, and 1.6, so right about there. And that looks pretty okay, I guess, because I got all this stuff over there to balance it out with the kind of left heavy stuff that I have here. So 1/2 and 1.6 visually kind of looks okay too. I feel comfortable saying that's the centroid.